7:02.
The Naked Scientist.
It's 23 minutes to 3 o'clock, counting down the sleeves to where Dr. Chris Smith gets his vaccination and comes back and tells us all about it.
Yeah, this Saturday. That's right.
By the time we speak next week, you'll have a whole story to tell.
Yeah. Well, I'm going to take my microphone along and I'm going to record the experience and document it for you. And then I'll come back and report back.
Wonderful, Chris. We've got questions lined up already and of quite a variety. So let's get straight into it. Joe has called us from Kilani. Joe, lovely to hear from you. Good afternoon.
Hello, Zania. Nice to hear your voice again. Hello, Dr. Smith. I want to ask you, if we were prepared, all things being equal, ready to go to Mars, how long will it take man to reach Mars? And when will the two orbits be so close together that we can attempt that movement to Mars?
Hello, Joe. The answer is that Mars is slightly further from the Sun than the Earth, and therefore the Earth takes slightly less to complete a lap of the solar system than Mars does. So the planets do line up periodically, and that's the time to go, because if you wait until they're lined up, then the journey between Earth and Mars is about 9 months. So these opportunities, there are windows for launches that come every year or two, and that's when the planets are going to be at their closest approach. And for that reason, most launches of probes and satellites and rovers are all timed for those particular windows. One just took off in recent months, actually. And we have timed that journey. In the past, people have made these measurements. It's about 9 months to get out there. And so it would make sense to send a rocket bearing humans to Mars in that window for the simple reason that you want to minimize the time that people are in space, in deep space, interplanetary space, because there is no cushioning and shielding from the Earth's magnetic field once you leave Earth's orbit and start heading towards Mars, and therefore you are potentially being hit by cosmic radiation. Now, craft are going to have to be endowed with some kind of protection against cosmic radiation, because the measurements that were made, NASA's Curiosity rover that went to the Red Planet about a decade ago, this is endowed with a radiation detector. And so the NASA scientists, probably with this very question in mind, turned on the radiation detector aboard Curiosity as it made the journey to Mars to see how much radiation, were a human sitting in that spacecraft, they would be exposed to on that journey. And it was basically half of an entire lifetime's safe working dose of radiation in that journey alone. So therefore, if you went and came back, you'd get your entire lifetime's worth of radiation dose just in that journey. So that's an unshielded spacecraft, or with minimal shielding against cosmic radiation. There will inevitably have to be some kind of protection put in place to fend off these particles, but no protection is perfect protection. So you want to minimize the exposure, minimize the dose. That means going when the two planets are in alignment, and it will take about 9 months for them to get there with current technology.
There we go. Joe, brilliant question. Thank you. Next, we've got Dennis in Fourways. Dennis?
Thank you. Stars that are born in the universe, where do they derive their matter from post the Big Bang? As we now know that you cannot create matter. Thank you.
Thank you for that question. Chris?
Well, the universe is about 13.8 billion years old. And when the universe was first formed by the Big Bang, it was small, extremely hot, far too hot, in fact, for any particles, and by particles I mean atoms, to exist. And as the universe inflated, because as things get bigger, they cool down because the energy is being distributed over a bigger volume. Eventually, the universe reached a point where it was sufficiently cool that, and I don't mean cool with shades and snazzy and pop star-esque, and at this point, atoms can begin to exist. So electrons and the other particles can associate together to make hydrogen. So most of the products of the Big Bang, hydrogen, a little bit of lithium and a little bit of helium. These particles then coalesce together because there's a random kind of distribution of this material throughout the growing universe. And under the impact of gravity, because anything with mass has gravity, these things begin to attract each other and fall together. And so out of that initial mishmash sort of soup of particles, you then get stars forming. And those first stars were absolutely enormous and fueled by hydrogen, very, very hot. And anything that is really big has really big gravity, which means it's really hot, which means it burns its hydrogen really fast, and then it explodes. at the end of a very short life, relatively speaking, for a star. And as it explodes, it showers the universe with shockwaves. But in those shockwaves, it also produces many of the other much heavier elements that we see in our periodic table in chemistry classrooms. So they go flying off into space, and then the process starts again. And there'll be other parts of space where, with a bit of that admixture of the dead stars and some of the other hydrogen that's floating around, the buffeting from stars exploding causes other clouds of dust to begin to collapse together, and you get a new star forming. And you get this process where you get areas of the universe forming stars, and you get and they're in galaxies, of course. And so there's these whole generations of processes: the first stars which have been and gone, then the next generation of stars, and the next generation of stars. And as they burn, they turn hydrogen into bigger elements through the process of nuclear fusion. And depending upon how big the star is, at the end of its life, it either burns out and turns into a sort of stellar cinder, or if it's big enough, it explodes, and it can cause a supernova. And when it does so, it can produce even bigger, heavier new elements, and in some cases collapse into a black hole, or in other cases collapse into a neutron star, which is another very dense object, a specialist object out there. But that's the evolution of all of these things, and they're using the hydrogen produced by the Big Bang to fuel those stars. But there'll be an added mixture of elements made by other predeceased other stars that predeceased them and have showered their cosmic neighborhood with the products of those stars' lifetimes.
Wow, Dennis, thank you. So fascinating. Next, let's go to Miriam in Pretoria. Hi, Miriam.
Hi, Azani and the doctor. I just want to find out from the doctor. I get the pleasure to chew white printing paper, and I just chew it and then swallow it. I get that pleasure, and always there's a desire to do that. I don't know, is it harmful or what?
White printing paper, does it have ink on it, or is it before it gets used?
Without ink.
Okay.
Just a white thin paper.
What I would say is that a tiny amount is probably going to do you no harm at all. But if you keep doing this and eat lots of paper, you haven't actually evolved to eat paper. There are some animals like elephants that can eat anything they like because they've got the digestive tract of an elephant, and it will just go straight through, and they have evolved to eat hunks of tree and branch and that kind of thing. And paper is wood, and you are basically asking your digestive tract to digest the indigestible, because our digestive tract doesn't have the right enzymes in it that can break down the woody bits of wood, which is called cellulose, and that's what makes paper stiff and rigid. And so when you chew up the paper, it goes into your stomach and you just can't digest it properly. That's not even considering that there are other things added to paper to make it nice to write on and print on, which probably are not very nice for your digestive tract. So I know you're saying you enjoy it and you feel it's pleasurable, but I would really try and avoid doing this, because in the long run, it could actually cause you some problems. So I would avoid eating paper if you can.
I often wonder, how do these things start? Was the paper so close to the face? And then maybe the smell, and then thinking, I wonder how that would taste.
It puts a whole new spin on the phrase consuming the media or digesting the news, doesn't it? But please don't do that, Miriam. It's not going to do you any good in the long run.
Thanks, Chris. Next, we've got Keith in Athol. Hello, Keith.
Hi, Doctor. I've got two quick questions relating to antibodies. When a person's been infected with COVID and the body produces antibodies, my first question, is there a correlation between the amount of antibodies produced and the severity of the viral load of the infection? And then the second question is, if an infected person's body has produced a large amount of antibodies, what is the benefit of the vaccine? Meaning, will the vaccine actually stimulate the immune system to produce more antibodies?
Hello, Keith. The answer is that, to take the first part of the question, is there a correlation between the disease you get and the antibodies you produce? The answer is that there is a strong correlation between the severity clinically of the disease you get and your antibody production. In other words, if a person has trivial illness, they tend to make a lower level of antibody in the bloodstream compared to someone who has more severe COVID. And those antibodies are preserved for a period of time, but they do fall off with time. And the REACT study done by Imperial College in London looked at 250,000 people and tracked them over time, and they found that there was a 25% drop-off in antibody levels over 3 months. So in other words, there were people testing positive who then began to test negative after a 3-month period, suggesting that your antibody titers do decline with time. Now, in terms of the potential benefit or otherwise of vaccination, because some people have got plenty of antibody and presumably therefore also plenty of white blood cells called T cells because they've been naturally infected, they presumably do, at least for a short while, have quite good immunity to coronavirus. And a recent study published from the UK last week called the Siren study actually looked at 20,000 people in the UK, and they were a mixture of people who had and people who hadn't been infected with the virus and who had or didn't have antibodies. And the researchers followed them for 5 months, and they were able to compare the rates of infection with coronavirus in both groups. And they found that some of the people who had antibodies still got reinfected with coronavirus compared to to people in that group who also had antibodies and didn't. So that tells you that antibodies aren't the whole story, and that having caught the infection, you can catch it again within 5 months or so. But there is a degree of protection conferred. That said, if you do have the vaccine and you're in that position, the vaccine is going to basically remind your immune system what it has learned already. It's like sending your immune system into the exam room and saying, right, okay, we're going to set you an exam to test how good you are at defending the body against coronavirus. And therefore, the worst that can happen if you have the vaccine is that you're going to give yourself a big booster and you're going to make even more powerful immune responses, which will protect you probably for longer. If you don't have the vaccine, the almost certain outcome is that you might already be susceptible to reinfection with coronavirus, or you might within the coming months become susceptible again. In either case, the vaccine will push that time of susceptibility way back in time, possibly for a year, possibly for longer.
Mm-hmm. Chris, thank you. We actually had a masterclass on that last week, on vaccines and, the level of protection that they provide versus the protection that you get if you had the virus. It was really fascinating. And this also, your answer actually deepens part of the questions that we had and the answers that we had in that masterclass. Thank you so much, Chris. Keith, maybe you can go back and listen to that masterclass as well if you have more questions on the vaccine. Here is one that came in on our WhatsApp line, and I did use this one to tease our segment, so I must honor this particular listener. That is Vusi in Leandra, and he says, my question for the naked scientist is why water rotates anti-clockwise in drains, bathtubs, kitchen sinks, and so on when released?
Well, actually, it's a myth that if you flush your toilet in the northern hemisphere, it goes in one direction, and you flush it in the southern hemisphere, it goes in the other direction, because this is actually a trick. And Michael Palin fell for this when he was doing his Around the World TV documentary, because they had some guy who had a bowl of water, and he showed that when he took his finger off, the water went down in one direction. And then he said, look, if I step over the equator, and they had some notional line on the ground, this is the equator, and he swung round towards the camera and then took his finger off. And of course the water went the other way because the guy was cheating. He'd swung round in a big circle, imparting spin to the water. This is the key thing, that when you have the local factors, like you impart spin to the water that's in the sink, in the toilet, in the bowl, and then you let the water go, because the water's got the so-called conservation of angular momentum, it's already turning and spinning in the bowl, it will therefore go down the plug hole with that spin. And the taps, when you turn on the taps in the sink, the cold tap is on one side of the sink, the hot tap is often on the other. So therefore the water will naturally have a degree of spin in the bowl already, so it makes a spiral when it goes down the drain. So it's usually a myth that the things rotate in one direction in the northern hemisphere and the other direction in the southern hemisphere in things like tanks, sinks, toilets. But if you do the experiment properly, it is real. And you can do this, and it is the same science that accounts for why in the northern hemisphere a hurricane, which blows up the coast of North America, will rotate anti-clockwise, and south of the equator tropical storms will rotate clockwise. And the reason this happens, it was demonstrated by researchers in the 1950s and in the 1960s in the southern hemisphere and in the northern hemisphere respectively. What the first person who did this in Sydney, I think it was called Trefethen, and the guys who did it in America, it was Shapiro is the first author on the paper. They published this in prestigious journals, and they had an enormous great tank a couple of meters across with a very small hole. in the bottom at the middle, and they filled it with water in each case and left it for a really long period of time so that any natural spin in the water would slowly settle out and the water was still. And then they took the plug hole out, and as it drained very slowly, you could begin to see that there was a spin. And in the southern hemisphere, it's a clockwise spin, and in the northern hemisphere, it's an anti-clockwise spin. So that's the experiment done very fairly and done properly. What it is demonstrating is this notional effect called the Coriolis effect. And this is because the planet is spinning, and because the planet is spinning in a big circle, things that are on the surface are also spinning. And as they move towards the equator, they can't not spin. So they were going in a big circle, and they move into a smaller circle, they can't not spin. It's called conservation of angular momentum. And the way the maths works out is that the way that they lose this conservation of angular momentum is that they spin in one particular direction. They feel a notional force which is in one direction in the southern hemisphere and the other direction in the northern hemisphere. And this Coriolis effect is a very real phenomenon, will give the impression of the water spinning in those two different directions. But you've got to do the experiment carefully and fairly. This is not the case with people's toilets and toothbrush sinks. It won't have that effect, so it's a myth that it works in your sink, but it will work if you do the experiment properly, and it definitely works when you scale it up to the scale of a hurricane.
Thank you for clarifying that, because, we could have just thought that it was a myth, but now we see that if done properly, that it is it is true at a hurricane level at least, and how the world spins. Let's take a listen to this voice note.
Hi, Asa and Chris, Jasper here from Lombardy. I have a question. Sometimes when I yawn or open my mouth wide, I release spit, right? But it's not intentional spit, as in I'm the one who's actually spitting, but it just happens on its own, whereby maybe some glands in my mouth or at the back of my tongue or wherever that releases their spit, but it comes out like the way a snake would actually spit on you. So I just wanted to find out, what is that? What causes that? Why does it come out when someone is yawning or something like that? I don't know if you understand my question. Thanks a lot. Cheers, guys.
This is one guy, if you've got him in front of you, you don't want to bore him, because you don't want to make him yawn, do you? The answer, Jasper.
Like a snake, it comes
Yeah.
out.
Well, I didn't want to call him a snake because I thought he might be insulted. Yeah. The reason this happens, most probably, is that there are a range of different salivary glands around the mouth. There's a big one which sits on either side in front of your ears. It's called your parotid gland, and there's a duct that runs across the outside of your cheekbone and then into your mouth cavity. But there's also some big glands called submandibular glands, which if you run your fingers under the angle of your lower jaw, you'll feel a bulge. Roughly when your fingertips are pointing towards your ears at the back corner, you'll feel a bulge there. There are some lymph glands there, but there are also some big salivary glands there, and there are some under the chin as well. When you yawn, you stretch all the tissues and all the muscles, and you inevitably will press on those glands. And in some people, just because of the way their anatomy works, when you yawn or move, you will press on your glands more than somebody else. And if you apply pressure to a tube which has got fluid in it, which is what the salivary glands are, they squirt the saliva into a tube which then goes into the mouth, it will push the fluid out of the duct and into the mouth. And there is one of the sites where the saliva enters your mouth is if you look in the lower lip, if you pull your lower lip forward, there's a frenulum, a little tag of tissue there that attaches your lip to the bottom of your tongue in your lower jaw, and the saliva's produced in the mouth there as well as everywhere else. And so probably what's happening is as he's yawning and curling his tongue back and squishing the glands, it's pushing fluid out and through that small hole, and it's going whoosh outwards. Normally it would squirt into the back of your teeth, but when you've got your tongue curled back, your mouth open, you're giving a really big yawn, which everyone listening to this is now feeling the inclination to yawn, because not because I'm boring, but because we all feel contagious yawning effects, and that is making him spray out saliva. So I think it's perfectly natural. Some people can do this, and just don't get bored around your friends just because they won't want to talk to you for much longer.
I'm doing a course in breathwork to be a breathwork practitioner, right? So we're reading all sorts of literature. One of the books called Breathe. Earlier I talked about one called Breath, but one called Breathe. The author has a beautiful chapter dedicated to the yawn, saying that society needs to change its attitude to the yawn and stop associating it with boredom. If anything, it's a great tool to shift energy. Just look at the effects after you've yawned. You can think more clearly and so on. And you can also bring on a yawn. You can just carry one out just by choice, at will. So it's definitely changed my perception of a yawn. I think I love yawns. I think.
Well, I've got a friend who's doing some experiments. He's trying to see if he can catch yawns off a hamster, and if he can get his hamster to learn to yawn when he yawns. I don't think he's succeeding, but the dog definitely yawns sympathetically. When he yawns, the dog yawns. So he's looking at different animals to see if contagious yawning works with them.
Yes. I'll try it with my puppy and I'll come back and report.
Let us know.
Yes. Chris, till next week, we'll have so much to talk about. My yawn experiment and your vaccination and everybody's calls, of course.
I'm looking forward to it. Thanks, Azza. Bye-bye.
Thank you. That is the Naked Scientist, Dr. Chris Smith. Robert the Deuce has said on Twitter, I fell for the equator trick in Uganda, even got a certificate. And there Chris was explaining exactly what was at play. I'm glad that we could clarify that for you, Robert. It is 3:00 and time for the latest in EWN. Till tomorrow.